Lastly, we'll talk about the common challenges that one would face when trying to build a machine learning model. One of the most common issues that a machine learning practitioner will face is the lack of training data. Human babies are remarkable because they only need a few images of an apple to learn and understand what an apple is. However, current machines are nowhere near at that level. It may take millions of example images for a machine learning model to correctly classify images. Often, you'll find that you can improve the performance of your model by increasing the number of training data. However, it may be very expensive and time-consuming to do so. The second problem is that your data may just be bad data. For example, there may be duplicates of the same data points, data is missing, data is inaccurate, or the data is just incorrect. In addition, your data may just consist of outliers or irrelevant features, or your data may not even be representative of the task that you're trying to solve. These attributes makes it harder for machine learning models to learn effectively. Remember, garbage in, garbage out. It will be your job to find good data and clean it to make sure that your model performs as well as possible. You will also encounter some issues when you train your model. Often, you will end up overfitting during training, which occurs when your model performs very well on the training data, but generalizes poorly to the data in the real world. This happens when your model is too complex relative to the amount and noisiness of your training data. You may also encounter the opposite problem, underfitting. This happens when the model is too simple to capture the underlying structure of your data. Here's an example of what underfitting, overfitting, and just right will look like. In the graph above, our model is trying to draw a line that separates the red dots and the green dots as much as possible. In the first graph, our model is a linear line that underfits because the model is too simple to represent the separation of the red and green dots. In the second graph, our model perfectly separates the red and green dots, but you can see that it overgeneralizes on the data. And in the last graph, the line is just right, as it correctly captures the line that separates the green and the red dots. Some solutions that you can try to address overfitting is to simplify or constrain your model so it doesn't overgeneralize on your training data. This will probably require trial and error. You can also gather more data, but as discussed before, this may not be feasible. And lastly, you can reduce the noise in the data by improving the way you clean your data. To address underfitting, you can do the exact opposite of what you do to address overfitting. For example, you can select a more powerful model or reduce the constraints on the model, and you can feed better features to the learning algorithm. We train our model on data so it can perform well on a real system and not just well on the data we trained the model on. In other words, we want our model to generalize well to new training instances. We could just train on our model on the development phase and then deploy to see how well that model generalizes. However, this may not be a good idea because a poorly developed model that is put into production can cost the company a lot of money. Instead, we opt to split the data into 3 pieces: a training, validating, and a test set. We train our model on the trained data, tune our model on the validation set, and finally evaluate our model on a test set. There are also other techniques of splitting the data, but we'll leave that to another time. You may be wondering, why not just use a single framework like neural networks to solve all your machine learning related tasks? Well, you can try, but it turns out that in 1996, the computer scientist David Wolpert proved what is now known to be the no free lunch theorem. The theorem essentially states that if you make no assumptions about the data, it is virtually impossible to know beforehand which model works best. In other words, machine learning engineers need to develop skills and intuition to know when it's best to use a certain model as opposed to another model. there is no one framework that will work in all cases. This is why machine learning is considered to be an art as much as it is considered to be a science. You are personally responsible for trying to test and figure out which model is best for a certain data set. Another problem that you will encounter when choosing what model to use is the trade-off between prediction accuracy and model interpretability. A model like a neural network that is more accurate is usually less interpretable, meaning it's harder to understand why that model made the choice that it made. Interpretability can be very important. For example, would you trust a medical diagnosis from a neural network without understanding why such a decision is made? On the other hand, in certain situations, performance may be more important than interpretability. For example, you may not care why your machine learning stock trading algorithm is working well if it's making you so much money. It is down to your own judgment to decide which is more important in your use case. Models that are intuitive, transparent, and interpretable are called white box models, whereas models that are harder to understand are called black box models. Generally, black box models performs better. That will be all for the basics of machine learning, and hopefully you've gained some intuition about what it means for a machine to learn. To make sure you understand the concepts, we recommend that you try and answer these conceptual questions.